This meeting is being recorded.
Hey everyone, my name is Eugene and I'm working on the XLA runtime, and I'm going to give high-level overview and some details of what the XLA runtime is and what is the future and how we plan to use it. So what today? So we don't have really a runtime for XLA today. So XLA CPU compiles to x86 native function. Basically, you get back a function pointer, and that function pointer has a very specific ABI. So if you want to call that function from your code, you have to pass all arguments as a voice ** argument, and you have to know all the details about XLA CPU internals and the ABI. So XLA GPU has a thunk sequence. I know some people are familiar with the runtime. It's basically a base virtual class. It has a single function execute on a stream, and different XLA operations are implemented as a different thunks. So you have a thunks for Cholesky, FFT, different thunks for convolution that internally fall back on cuDNN NVIDIA libraries. So one problem with the XLA GPU that we have today, that's like all or nothing approach. Everything in XLA program should run on GPU, or everything should run on CPU. It's really impossible. It is impossible to express XLA GPU program that does some part of the computation on the host and some part on the device. So everything must go to the device, and all arguments and results to thunks must be inside device buffers, inside allocations. So there's no concept of thunk argument or thunk result. So thunks, they can't talk to each other. They can share the data only by writing and reading to device buffers, which is another limitation why you can't express some non-trivial control flow on the host. So in the new runtime, the goal is to unify executable artifact. So we want to produce the same thing that we can execute for all XLA backends. So we want to share more code between XLA CPU and XLA GPU. So the idea that we shouldn't have like XLA CPU and XLA GPU separate backends. It should be just the XLA compiler that can produce a binary that can run on multiple devices, that when beneficial runs part of the computation on the host and offload whatever is beneficial to devices like GPUs. So the XLA runtime for XLA programs, the goal is to compile HLO modules, XLA programs, to always to a native host executable with the help of LLVM JIT compilation. So you can think of that we take for GPU, we take a thunk schedule and produce an x86 function that we can serialize. So the benefit of this single executable that we can have an AUT compilation for GPU and for CPU, and we can save this, load it back later. And instead of exposing this voice ** ABI to the client, the XLA runtime will provide a C++ API for the clients of XLA to invoke precompiled XLA executables. So you shouldn't be passing pointers to some memory location on device or on host. You will be passing buffers, memrefs, tensors to XLA program through a nice to use C++ API. And you can think of XLA runtime like a libc. So to run a compiled C program, to allocate memory, to write on disk, you have a libc library that provides functionality and integration with the operating system. And XLA runtime is somewhat like libc for XLA programs. If your compiled XLA program wants to launch an asynchronous concurrent task on a thread pool, XLA runtime will provide an API for compiled program to launch tasks. And the same for returning results back to the client. So if your compiled program wants to return a tensor to the XLA client, the XLA runtime will provide an API for returning values, writing like through the memory, and XLA runtime takes care of converting whatever your compiled program returns to high level like tensor type, XLA buffer type. And XLA runtime defines its own FFI mechanism for defining custom calls. So unfortunately, it's called custom call like the custom calls we have today in XLA, but they are very different. They are type checked. So right now, custom calls have a very simple C API, and you don't have any type information, and it's very easy to misuse and get a seg fault at runtime. The new runtime will provide a fully type-checked custom calls that can verify the number of arguments, the number of returns, the attributes, and will do all the encoding, decoding in a type-safe way. And the idea that instead of thanks, everything becomes a custom call. So if you, for example, in XLA GPU, the runtime layer that provides integration with the device will be a hardware abstraction layer that you can define your own hardware abstraction layer for your own backend. So for GPU, we have an abstraction layer that is based largely on the stream executor and CUDA, cuDNN libraries. So the workflow looks something like this. So you have your input MLR dialects, stable HLO. For in the future, right now, for GPU, we rely on LMHLO and LMHLO GPU. So the client of the runtime defines the compilation pipeline that takes some high-level MLR dialect or combination of dialects, and eventually it should produce an LLVM IR dialect in MLR. So we can feed this IR to LLVM compiler. It will produce an executable, just an ELF library, and plus some metadata about the entry point of this native function, like how many arguments, how many results, what are the types, what are the dimensions. And all device kernels, GPU kernels, for example, will be in the part of like constant section in this ELF library. And so it will be fully self-contained executable that you can serialize and ship over the network, and you should be able to load it on in the different process and link it with the runtime primitives, and you should be able to run it on another GPU. So right now, the ELF file constant section has a PTX and cuBIN, and it means that you can start your XLA program in like a few milliseconds. And XLA Runtime, it relies on the LLVM org dynamic linker to load this ELF file. It links it with the runtime primitives, like you link it with the libc. And for XLA GPU, XLA provides its own like hardware abstraction layer with different custom calls that implement device abstraction, like launching a kernel, launching convolution, launching jam, stream synchronization, memory copy, and things like that. So the high-level picture is something like that. So if you have a JAX TensorFlow that use XLA as a library, they will probably talk to XLA through PjRt client. It's going to be device API. In the future, there's some work about like refactoring PjRt client, and PjRt client will talk to XLA GPU executable, and the runtime has another executable, which is an implementation detail of the GPU. So the clients of XLA, they shouldn't even know that we have this runtime thing. They should talk to XLA only through high-level PjRt client API, and GPU executable itself, it composes. So GPU executable defines a GPU hardware abstraction layer that consists of cuDNN, cuBLAS, CUDA custom calls, plus it has a default ABI and async runtime for concurrent execution provided by the XLA runtime, and altogether is linked at runtime and hidden behind the GPU executable APIs. Okay, is there like a question? Is there a persistent format for storing XLA executable? Yes, it will be basically an ELF. We can serialize an ELF file plus we add some metadata. It's a protobuf, like protobuf ELF file plus some metadata. So that's how we define the custom calls in the runtime. So they're fully type checked. So on the left, you have the function declaration. So inside your MLR model, you define a function call declaration in standard function dialect in MLR, and you add an attribute RT custom call, and you define the custom call name. So you can use all the types you want on the left, like for example, C, memrefs, and attributes like binary passes cuBIN. And on the right, you define the C++ signature of your custom calls. So you see, you don't have like voice star buffers that you had in custom calls today. You have you can return the status to return error message back to the caller. You have stream executor. You have memref as the types. And for example, for the launch custom call, you have a cuBIN and multiple variadic arguments. And it's all type checked and much easier to use than what it was before. So that's roughly how it looks like. So the first function on the top, the green one, you have your C++ function with C++ types. Then you define the binding, how to bind at runtime your gem custom call to this C++ function. Everything is explicit, so you have to spell all the arguments, attributes, and types of the arguments and attributes. That is, so we can derive it from the C++ function, but we don't want to derive it. We want everything to be very explicit, so everything is type checked at runtime. And then you can package these like custom calls into a library. So in this example, we have XLA Runtime library that has just one gem custom call that is implemented with this C++ function. At runtime, so because we can't really pass like arbitrary C++ types across the ABI, the XLA runtime defines its own ABI for custom calls that is stable and trivial. So we rely on C++ standard layout or C POD structures that the compiler pass. So the MLAR lowering pipeline that lowers to LLVM knows how to take a memref and encode it into a struct, LLVM struct. And when we execute the program, we have the corresponding C structure that is guaranteed to have the same memory layout. So we can safely take a pointer that we get at runtime from the compiled program and cast it to the struct and then decode it back to some nicer to use C++ types, because you don't want to pass around this encoded memory of C structs. You want something nicer with types and templates. And at runtime, we use manual memory packing, basically arguments passed on the stack. We pass the number of arguments, then we pass the type ID of the argument, and then we pass a pointer to encoded memref. And we can do it for custom user-defined types and arguments. So it's all extendable. So it's not only memrefs. You can pass your own custom type. You just need to define how your custom type is lowered to LLVM struct and what is the type ID of your LLVM struct. And it all, so attributes encoded in the constant section of the L file, it has this almost the same layout. So we have a number of attributes, then with the type ID, what is the type of the attributes, then the name of the attribute, and pointer to the value. And at runtime, we rely on this additional metadata to safely decode arguments, attributes, and we have roughly the same type of memory layout for results. Yeah, so encoding is extensible. So for example, on the left, you can see convolution and you pass MHLO attributes to your C++ function call. So you have activation, it is an MHLO activation, some window attributes, strides and dilation. So you just have to define declarative encoding. So how you take this MHLO MLA attribute and how you pack it in memory. And then you define your C++ enum and struct for window attributes. And then you declaratively register how to decode based on the type ID, how to decode memory into C++ type. And at runtime, you can bind these attributes activation and window to your C++ function handler. And yeah, so on the bottom left, you can see how the custom call binding looks like. So you don't really need to know about all the details of this ABI encoding. Everything is handled for you declaratively through few templates and helper functions. Yeah, I'll get to the question. So shape dimension checking done at runtime? Yes. So because we know the signature and we have the memref data type for arguments, we can do type checking. So all the statically known dimensions match the dimensions in your signature. And for all dynamic dimensions, we can accept any dynamic dimension. Also, XLA Runtime has automatic recompilation and specialization. So I'm not going to talk about this today, but basically you can define that for this particular argument, I need to know the static shapes. And once every new input comes with the new static shapes, XLA Runtime will automatically specialize your IR. So it will propagate all the shape information through your function and compile it. And you can specialize it to values. For example, if you have transpose or reduction with a dimension that is not known at compile time, but for efficiency, you have to know the reduction dimension at compiler time. So you can automatically recompile automatically, once you get the new value for the reduction dimension, you specialize your executable to that particular constant and do recompilation. And that's all handled automatically. You just need to define the MLIR pipeline that knows how to respecialize your input based on the newly discovered static information. And then runtime should handle everything else automatically. So one of the things that the new runtime allows you to do is to define async functions. So for example, if you have some execution on the host, like sparse dense matmul, that is not implemented on the device, you want to run two sparse dense matmul operations concurrently, and once they're done, launch something on the GPU. This should be expressible with MLIR async dialect. So instead of returning tensor of some value, return an async value, which is basically a future that at some point in future, this value will hold a tensor of unknown dimension. And inside your program, you can async execute. Basically, you launch two sparse dense matmuls, you get back two async values with tensors from the host, and then you can do async await and extract the value from the future. And once the value is available, you launch the kernel. So it looks like async await is a blocking operation, but behind the scene, it compiled to, like through LLVM coroutines, it compiled to asynchronous state machine. So the idea that you never have to block your main thread of execution. So once you see an async await of the async value that is not available, you suspend your execution and you register a callback. So once the value becomes available, please continue with like the continuation, everything that goes below async await. And at C++ level, so the async value that you can see in MLIR IR, at runtime, this will be the async value of your C++ type, and async runtime takes care of converting like whatever the tensor or memref at IR level in your MLIR program. The runtime takes care of converting that to your C++ runtime representation, your own runtime tensor like XLA buffer. We have integration with TensorFlow runtime. So basically you can take your whatever you have in your IR and automatically convert it to the TensorFlow tensor. But it's not that important for XLA because XLA has its own like buffers. So what is like the current status? So for XLA GPU, it passes all internal tests. So the current plan is to enable it by default in October, unless we find something that we don't know. But right now it relies a lot on the current emitters for device compilation. So the XLA runtime invokes XLA GPU IR emitters that emit device kernels, and then it takes those device kernels and packs them into ELF file. It's basically, we don't have anything new with regards to compilation. The goal is to do everything end-to-end in MLIR somewhere in 2023. So for XLA CPU, the work in progress passes around 60% of the tests, and the goal to have correctness parity with current XLA in Q4 and hopefully enable somewhere early in 2023. And we hope to get, so the plan with the new runtime, like the big feature of the new runtime is async execution. So XLA CPU today is sequential. You can run some of the parallel loops concurrently, but you can't execute multiple operations concurrent with each other. And in the new runtime, it should be easy with async execute and async values. So we think that once everything will land, we should get nice performance improvements just because we have an opportunity to do more work concurrently. And for XLA, it means that XLA CPU and XLA GPU, like there shouldn't be like hard boundary between CPU and GPU. It should be just the XLA compiler that can produce your host executable that itself can launch device kernels or run something on the host. And XLA should be easy for XLA to move computation between host and device, depending like on the shape, on the, for example, if you have a while loop with some simple computation in the condition block, you right now with thunks you're forced to run everything on the device, but conceptually you should be able to run your condition computation on the host. You might be able to duplicate some of the operations from the body to the host. It might be beneficial. It's not doable today, but with the new runtime, it should be relatively easy to do, just few compiler passes and analysis. And that's it about runtime.
Excellent. Thank you, Eugene. We're going to leave the rest of the time for questions. And I'm going to follow up. Taylor and I are going to follow up with an email on next steps. But we want to make sure you have time to ask your questions. So please go ahead.
Yeah, I see the question about the ROCm. I think yes. So Kubin and PTX is very NVIDIA specific because that's what I see most of the time. But basically for device, if we can put any device kernel in the constant section. So if AMD GPUs can produce, AMD compiler can produce a device kernel as basically an array of bytes, and the driver can take that array of bytes and load to the device, we can do it with a new executable format. And the same for TPUs. Basically, the TPU program becomes a part of the constant section of your host executable and the driver that knows how to load your device kernel on the device and how to run it.
Okay, thank you.
Do we have any more questions related to runtime, stable HLO?
So yeah, what will drive the XLA runtime decision? So we don't know yet. So in TensorFlow, we have the placer, and the placer is very hard to work with. So I don't think that we want to make these automatic decisions in XLA, because I think largely the consensus that it wasn't, well, not a mistake in TensorFlow, but it's very hard to work with. So I don't know how it's going to look like, but I hope it will be more explicit because automatic partitioning is very hard to do. Yeah, so the persistent format is ELF file. So on Linux, this is an ELF file. Basically you have your function pointer, your object file loaded in memory, and it linked with the runtime primitives. So you can take this object file, save it on disk, and when you load it back later, you just need to link it back with the runtime. So you have a list of symbols that are not resolved, like allocate new tensor through XLA memory allocator, or launch a concurrent task in XLA thread pool. You have to load your ELF file and link it with just those two functions. And metadata, so the XLA executable, when it is persisted, it will have the metadata, like what are the symbols that are unresolved, and the runtime will have to provide all those symbols when it's loading an AUT compiled binary. So what about Windows? I think it passes all the tests today. So everything is in open source. It's available under compiler/runtime folder and XLA/Malaya transforms runtime. So it's all the same. So LVM org, LVM grid compiler, it works just fine on Windows. So whatever the object file that Windows uses, we will persist it. So it's not going to be ELF, it's going to be Windows object file. And then when we load this object file, it's all the same. We just get the object file that is not linked, we link it with the missing symbols, and we should be able to run it.
Any more questions? Last call for questions, and then maybe we have some time to briefly discuss what our next steps are. Oh, something from Ashok?
I had another follow-on question about, do you have any plans for heterogeneous executables for both device? For example, if you have some system where you have both x86 and ARM machines and different kinds of accelerators, you would
I
like
think
to
our current plan that you have to define the spec of your machine upfront. So you have to define, so I have the NVIDIA GPU or Intel GPU, like whatever GPU plus the version, plus the version of the instruction set. And we can compile executable for that specific machine. Yes, I think we can produce executable for multiple instruction sets, but I don't think that it's like on our radar. I don't think that we plan to do it because it adds quite a lot of complexity, and it's just easier to recompile. So there's a question about ARM. So yes, we plan to support ARM. So if LLVM org supports ARM, if we can, basically, if there is a compiler, LLVM can take LLVM IR and produce an executable, an ARM executable, it should just work. So it doesn't require anything specific from our side because we rely on LLVM. I don't think that we test. Well, I think I've seen that. I think we started testing something on ARM. I've seen fixes for ARM last week. So we ran some tests on ARM, and I think it works, but that's not like the priority. But it should just work. So
I mean, for shipping it, I know that TensorFlow supports Mac M1, which are ARM64.
Yeah.
So it's going to be on the path of shipping anyway. Like by default, we have to support ARM. And as Eugene said, like there's nothing is specific to x86 in what we're doing. It's very abstract and very using the vanilla LLVM features, the same one that Clang is using. So if Clang works with coroutine, for example, on a platform, then like the only thing specific we're using from LLVM is the coroutine infrastructure.
Yeah, and it is part of LLVM. It's not part of even Clang. It is LLVM, and it was there for a couple of years. I think it's tested rather well. So we don't, I don't expect to see any surprises.
Fantastic. So we're almost at time. Mehdi, do you want to go to the last slide and I'll give a brief update on
I'm
it?
going to stop the recording here for the runtime. Thank you, Eugene, for this presentation.
Yeah, thank you, Eugene.